Let's go ahead and do it. So directional derivative, we need two things. We need the gradient at the point, and we need the direction as a unit vector. So here's my gradient. My gradient as a function is just the partial derivatives as a vector. Sorry, I should say the gradient as the vector function. Gradient in terms of my variables is going to be the x component is going to be 6x to the 5th y cubed. The second component is going to be x to the 6 times 3y squared. And then at the point, the gradient of f at the point 1, -2 is going to be, let's not write it all out. It's going to be 6 times 1 to the 5th, which is 1, times -2 cubed. So 6 times -8 is going to be -48. And here we have 3 times 1 to the 6 is 1, times -2 squared, 3 times 4 is 12. And our unit vector, so v is -5i plus 2j. Let's just go ahead and write here that u is going to be -5i plus 2j divided by the magnitude of that vector, which is the square root of -5 squared plus 2 squared. That's 25 plus 4 is 29. So I can write that as -5 over root 29 I plus 2 over root 29j. There usually isn't any great kind of desire to rationalize these denominators when you normalize a vector. So I wouldn't encourage you to do it unless your teacher is really, really impressing upon you that you should. Finally, our directional derivative is going to be that vector dotted with that vector. So it's just the gradient of f at the point 1, -2, dotted with the vector u, which is going to be, again, I've obviously I'm using some mixed notation here. That's really okay. I guess I'll put it all together in one. So -4812 dotted with -5 over root 29, comma 2 over root 29. -48 times 5. Who multiplies it? So easy way to multiply by 5, multiply by 10, and then divide by 2. So you can get 480 divided by 2 is 240. That's going to be 240 over root 29, and it is positive, it's a negative times negative, and then 12 times 2 is 24 over root 29. So we're looking at 264 over the square root of 29. Some follow-up questions for this function around this point. So there's a few typical types of questions that we might ask, like, what is the maximum value of the directional derivative at the point 1, -2? The answer to this question is always the magnitude of the gradient. So whenever they're asking you what's the maximum value of the directional derivative, or what's the maximal rate of increase or rate of change or slope or whatever words they want to use to indicate this thing, it's always your gradient. It's always it's always the magnitude of your gradient. So the answer here is the magnitude of the gradient at the point, which is going to be the square, let's see, no, it's going to be kind of gross. It's going to be the square root of -48 squared plus 12 squared. Which is, okay, not the nicest thing ever. I think it's 720. Find out. Let's see, 148 squared plus 12 squared. No, definitely not 720. 2,448. Oh, I know what I did. Cool. It's a very large value, right? I mean, it's kind of it's pretty close to 50. Okay, here's a more interesting question. What is the minimum value of the directional derivative at that point. Anyone want to venture a guess? You don't have to guess, but if someone thought they might know, I would entertain your guess.
-2.
Negative something. Oh well, so not yeah at the same point, right? So let me phrase it this way. I'm asking you for the smallest value the slope could have, and I will point out if I'm walking up the hill in this direction and the slope is the steepest, if I turn around, now I'm going down the hill, the slope is as negatively steep as possible, and it's the same value, but negative. Exactly. The minimum value of the directional derivative is the negative of the magnitude of the gradient. Sometimes people will phrase this question as like someone actually skiing on a slope, and they'll ask you like, what slope will you be going down if I go down the hill the fastest? They will probably actually ask you what direction you should travel in. So follow up. What direction? Let me make sure I phrase this right. Right. In what direction does the function f of xy equal to x to the 6 times y cubed increase most rapidly at the point 1, -2? So I'll remind everybody, the maximal increase is the magnitude of the gradient. The direction that you get that maximal increase in is the direction of the gradient. So now here's where your answer might differ depending on who you are, what your teacher wants. You might just say it's the gradient at the point 1, -2, which we already calculated. It was -48, 12. Or as a unit vector, we could do -48, 12 divided by the square root of 2,448, which you could write as -48 over the square root of 2,448i plus 12 over the square root of 2,448j. Right, if you've already found the magnitude of the gradient, then normalizing the direction of the gradient is really, really easy. You just take your gradient vector and divide it by the magnitude of the gradient. And I would say this is probably more likely to be the answer someone's actually asking you for. I will quickly point out, what if they'd only asked us for the direction and they wanted it as a unit vector? Let's pretend we had done none of this work and all we knew was that we had to take this vector and normalize it. I don't really want to do that vector divided by the square root of 48 squared plus 12 squared. I want to remind everybody that this vector here, -48, 12, points in the same direction as any multiple of it. So I could say maybe divide every component of that vector by the same number. And those two numbers have a lot in common. I could divide them both by 6. I could even divide them both by 12. 48 divided by 12 is 4. 12 divided by 12 is 1. So this points in the same direction as the vector -4, 1, which is a lot easier to find the magnitude of, I think. So I'll say that the magnitude is the square root of -4 squared plus 1 squared, which is the square root of 17. So another equally good answer would be, instead of this vector divided by this magnitude, sorry, you guys can't see what I'm writing here. I'm gonna do this vector divided by its magnitude. You get -4 over the square root of 17i plus 1 over the square root of 17j. And just to really satisfy everybody's potential curiosity here, hopefully you can't see that, that's terrible. I will just point out that 12 divided by the square root of 2,448 on my calculator is about 0.2425, and 1 divided by the square root of 17 is 0.2425. They are the same number. So really, if you're normalizing, right, making a unit vector out of something terrible like this, get it down to something easier. Get a multiple of it, and then normalize that. I think that's easier. Okay, last question about this particular example. In what direction? Sorry, I'm squeezing things at the bottom here. In what direction does f of xy equal to x to the 6y cubed decrease most rapidly at the same point? All right, the same thing I said before still applies. If I'm going this way and increasing the most rapidly, the way I decrease the most rapidly is by, right, turning around. And when you turn around, the vector you had is just the negative of what it was. So my direction is going to be +4 over root 17i minus 1 over root 17j. Excuse me. Let's look at one more directional derivative thing. Someone asked specifically, actually, I should say, are there any questions about this before we move on to another example?
Okay, but with the orange and
It's totally fine to write it this other way I'm writing. I mean, there's lots of ways you can write a vector. It's also fine to write it like this. I would say these are the two kind of standard ways, in my opinion. But honestly, like, let me just point out, there's probably 5 good ways you can write a vector. The vector v, you can write it as 3, 4, or 3i plus 4j, or you could use a column vector. You could also write it as a row vector. And some people unfortunately use terrible parentheses, which I would never use. These are all ways of indicating the vector that goes over 3 and up 4. I would say you should never use this, because it's really easy to confuse with a point. But that's also why people use it though, because sometimes you're thinking about the vector as the thing that starts at the origin and ends at the point that is exactly over 3 and up 4. This notation, this column notation like this, we will also use quite a bit actually in this class as we go on. So I would say this one, not so much. I would not use this. And I will point out there is no comma there. So I'm writing that like a matrix. But I probably wouldn't use that either. But these 3 here are all pretty standard. But really, as long as what you're writing is relatively clear, what you're doing should be fine. Something else I want to say then? It's not. Let's look at one more example with a function of 3 variables. Let's say that we are given f of x comma y comma z equal to, let's not make it too terrible, 3x over 4y plus 6z. And we want to find the derivative of f at the point. Sure, let's go. Well, let's be smart, James. Let me think about this for a second here. At the point 8, 1, 3. Sure, that should turn out okay. in the direction of the vector of v equal to, what have I got here? 2i minus j plus 2k. So I and j when it's, so again, like, just like here, you can write this as 2i minus j plus 2k. You could also write it as 2 comma negative 1 comma 2. You could also write it as the column vector 2 negative 1 2. All of those are perfectly valid. Notably, I don't want to write it using parentheses because I just used the parentheses notation to indicate a point. Yeah, we'll talk about this a little bit. So it's the usual calculation, whether it's a function of 2 variables or 3 variables or however many variables. It's always just going to be the gradient at the point dotted with the unit vector in the direction we're going. So the gradient is going to be kind of gross here. I might choose to write my function as 3x times 4y plus 6z to the negative first, so that it's slightly easier to take my partial derivatives. So my gradient here, just without plugging in the points yet, the partial with respect to x is the easiest one. That's going to be 3 times 4y plus 6z to the negative 1. The partial with respect to y and z are going to be a little bit less nice. With respect to y, it's going to be 3x times a negative 1. So let's say it's a negative 3x times 4y plus 6z to the negative 2 times the derivative of the inside, which is 4. Similarly, you should all be able to figure out what the partial derivative with respect to z is. It should be almost the same, a little bit different. I'll give you 20 seconds. Enough time. Instead of multiplying by 4, I'm multiplying by what? Right, but the rest is the same. Right, I had some stuff to the negative first, and the derivative was negative 1 times my stuff to the negative second. And then at the end, I multiplied by the derivative of the inside, and that was 6 over here where it was 4 over here. And that is probably going to be kind of gross, I'm not gonna lie, because I picked gross numbers. So my gradient evaluated at 8, 1, 3 is going to be, man, okay. So y is 1, and what did I pick 1? Oh, that was smooth, James. I think I was, wow, I was imagining different numbers. Wow, yeah, that's not what I thought was gonna happen. You know what I can do though? Wow, yeah, how did my brain do that? I was really sorry, my brain was like really thinking something different, and like I don't know what happened. But what I wanted to happen was something different. Let's I'm gonna change it just slightly since we haven't plugged in the number yet, right? It's not a huge crime. I'm gonna change my point. Yeah, right. It's not gonna affect anything terribly. I really want it to be not 813. I want it to be, what do I want it to be here? I want it to be 832. Sorry. But I'm doing it for you and for me. So the numbers don't come out to be quite so terrible. So let's see what happens when we plug this in. I mean, it's probably still going to be awful. Let's see. So I'm plugging this in. I do like rewriting this as fractions. So instead of writing 3 times this thing, first, I'm going to write this as 3 over 4 times 3 is 12. 6 times 2 is 12. Over here, I'm going to get negative 3 times x, and negative 3 times 8 times 4. And I know my denominator is going to be 4 times 3 is 12, plus 6 times 2 is 12, but it's going to be 12 squared. And finally, over here, a negative 3 times 8 times 6 over 12 squared again. I could probably simplify this a bit. 3 over 12 plus 12 is 1 over 8. This is not the important part. right? I'm simplifying this because I want to make it easier to deal with, but this is really not the part we should be focusing on here. So let's just, so I'll point out 3 times 4 is 12. 12 over 12 squared, one of those 12s cancel. I'm left with 8 over the other 12, which is really just 2/3. Except it's negative 2/3. And finally, same deal here. Same deal here, James? Sure. 3 times 8 is 24. 24 over 12 gives me a 2. 2 times, oh, this is exactly 1 over here. Well, negative 1. You can check. 8 times 6 is 48. 3 times 48 is 144. And 12 squared is 144. So it worked out. It could have been better, but this is not the worst thing we've ever seen. So then we also have to take our unit vector, sorry, our vector, and make it a unit vector. So our unit vector is going to be the vector 2i minus j plus 2k divided by the magnitude of that, which is going to be the square root of 4 plus 1 plus 4, which actually turns out pretty nice. That's going to be square root of 9, which is 3. So 2/3, comma, negative 1/3, comma, 2/3. You might notice, I'm not doing this on purpose, I'm just doing it because I find it easy to. I switch back and forth between notations a lot. Of course, yes, sorry, yeah, I'm sorry, I zoomed in to try and make it easier to see, which was for a while. But yeah, it's totally okay to switch back and forth between notations, just try to be clear with what you're doing, as I will try to be. Finally, we're ready to take the dot product of our gradient and our unit vector. So our directional derivative is going to be the dot product of our gradient at the point 1/8, comma, negative 2/3, comma, negative 1, dotted with 2/3, negative 1/3, 2/3. And multiplying this out, so 1/8 times 2/3 is going to be 2/24 or 1/12. Negative 2/3 times negative 1/3 is positive 2/9. And negative 1 times 2/3 is negative 2/3. And I might just choose to leave it like that. But we could simplify it if we really, really felt the need to. But I don't feel the need to. Yeah. I secretly do though. Yes. What if you're given an angle? Good question. So for example, let's see if I have an example here. I don't think I do. So for example, we're given a function an angle. Okay. Right, yeah, I'm just trying to think about how you would how someone would ask a question where I can ask a question where we're asked to find the angle between two vectors, but I don't think that's what you're really asking for.
Yeah.
You're asking more like, how do we find the directional derivative if we're given an angle? And we're given a function. So let's say I'm gonna make a function where it's gonna be not too terrible. Let's say our function is x cubed minus y, the 2y squared. And we want to find. Let's think about it. So we want to find the directional derivative at the point. Let's go, yeah. 2, 1. In the direction of, I'm going to phrase it this way, of theta equal to 2 pi over 3, where we're measuring from the x-axis. So for example, right, I'm kind of looking at it like this. I'm taking my directional derivative at the point 2, 1, and then I'm going in the direction of the angle 2 pi over 3 from the horizontal. So this is like theta equals 0, and that is going to be like theta equal to 2 pi over 3. Is that kind of what you're getting at? Okay. So great. here's what we're gonna do. We're gonna use the alternative version of the formula. Question? No, sorry, you kind, it's all right, that's right. So instead of finding the directional derivative as the gradient dotted with the vector, the unit vector, instead, it's going to be the magnitude of the gradient times the magnitude of the unit vector is just 1 times cosine of our angle. I will also talk about how we can find the unit vector u in a second, but this is how I would probably do it. So we still have to find the gradient. The gradient of f is going to be the vector 3x squared in the I direction minus 4y in the j direction. My y kind of looked like a j there, apologies. And then plugging in my point, my gradient at the point 2, comma 1 would be 3 times 2 squared, so 12i. 4 times 1 is 4, so minus 4j. And then the magnitude of that, I feel like I'm getting a lot of 12s and 4s today. The magnitude of my gradient is going to be the square root of 12 squared plus 4 squared, which is, technically I should be writing 12 squared plus negative 4 squared, but we know that when you do have negative squares and positive. That's going to be 144 plus 16, which is 160 in my square root. And then we have to multiply that by cosine of 2 pi over 3, which we are kind of expected to know. So I'll remind everybody that cosine of pi over 3 in quadrant 1 is positive 1/2. Cosine of 2 pi over 3 is negative 1/2. That's going to end up being the square root of 160 times negative 1/2. And you could probably, we could simplify this a bit if you wanted to. We could rewrite this as 16, that's a 16 times 10. So really that's the square root of 16 times the square root of 10 times negative 1/2. So you can write it as negative 2 root 10 if you wanted to make it look a little bit nicer. Because that is the formula for the dot product. So when you take the dot product between two vectors, it is the magnitude of the lengths of the vectors multiplied by cosine of the angle between them. On the other hand, there's something called the cross product, which is something we really talk about in this class. And that's where you multiply by sine of the angle between them, not cosine of the angle between them. Yeah. Another way to do this would be to say, so it would be actually to find the unit vector u. So if you want to find this unit vector that points in the direction of theta being 2 pi over 3, well, you could really just look for the point on the unit circle. And say on the unit circle, if my angle is 2 pi over 3, the point there is the x coordinate's negative 1/2. Anyone know what the y coordinate is? It always goes with 1/2 on the unit circle. Square root of something over 2. Square root of 3 over 2. So alternatively, we could have done this by taking the dot product of this unit vector with our actual gradient. And if we did it that way, then, sorry, I'm like writing things all over the place here. If I did it that way, I'll just write it right here. It would have been my 12i minus 4j dotted with negative 1/2 I plus root 3 over 2j. Now I want to calculate this because it looks dicey. I am having a hard time convincing myself without doing the work that dot product is going to be the same as that number there. So let's check it out because I think it's worth seeing that. I'm hoping that I feel like I hope I didn't make some stupid mistake and it turned out to be the same. Let's find out here. So that square root of 3 is really worrying me. Oh well, so 12i minus 4j dotted with negative 1/2 I plus root 3 over 2j. So just multiply that part together, so you get 12 times -1/2, which is -6. And minus 4 times root 3 over 2 is going to be -2 root 3. Well, at least they're both negative. I'm a little worried though. I feel like that's geez, yeah. Are those the same? I don't think so. I'm gonna have to think about this because I don't have a good, and I'm not, let me make sure I just didn't make a stupid arithmetic error here. That's 144 plus 16, right? That's 160. 160 is 16 times 10, square 16 is 4. That all seems okay. I just want to make sure I didn't make some dumb mistake here. I hate it when I get caught in a dumb mistake. 3 times 2 is 12, 12i. J. That all seems right. Let's just double check. Yeah, that seems okay. -4y, that seems all right. At the 0.21. Well, darn, I hate it when they don't come out the same because yeah, and my gradient of f, let's make sure the gradient's right. Gradient is, that's right, and then we're dotting it with the unit vector in the direction we're going. Well, darn it all. Anyway. Yeah, that seems super funky. Let's look at the calculator just to be absolutely sure, and then I will stop thinking about this and I will try to figure it out later and figure out what exactly I was thinking. Yeah, they're definitely not the same. Yes.
But I thought you-
Uh-huh.
like fx, parentheses x comma y cos theta plus fy x comma y sine theta, and I got that from the book.
So one more time.
It's
Well, yeah, no, that's yeah, that makes sense, actually.
this is one of my lessons, because I didn't know how to do this question, but they did like.
So that is the same thing I'm doing though, or let's say the same thing I'm purporting to do, right? Because here's what I'll point out. So let's take a look. Might as well answer all the questions. So I'll point out here that maybe the way I was thinking of this is wrong. But right, the fx thing you're thinking of, right? What's fx in this function? 3x squared. What's fy? -4y. The point I picked was the point 2, 1. So fx at the point 2, 1 is going to be 3 times 2 squared, which is 12. Fy at the point 2, 1 is going to be -4 times 1, which is -4. So that's my 12 and my -4 that I'm writing in as my gradient right there. And then you said times cosine of the angle and times sine of the angle.
Yeah.
Right, so our fx at 2, 1 times cosine of 2 pi over 3, that's going to be 12 times, I got my cosine right? 2 cosine 2 pi over 3 is definitely -1/2. And then, which is going to be -6. And fy at 2, 1 times sine of 2 pi over 3. Sine of 2 pi over 3 is definitely root 3 over 2. So it's, oh. No, I thought I found a mistake. I was very excited for a second. -4 times root 3 over 2, which is just -2 root 3. And then you add them together, right? So it looks like this answer is correct. So clearly I'm thinking about something wrong the other way, and I don't know what it is. That's annoying. I'll figure it out and mention it later. Sorry about that. I don't know. No, yeah, it's gonna bother me. Oh, well. So we only got 15 minutes left. We should probably talk about a few other things. Someone had mentioned they had a question about the quiz. I hadn't looked at the quiz, so we can say that till Wednesday. Let's talk a little bit more about maximizing and minimizing because that's something you talked about today. So, reminder to everybody, we're going to maximize / minimize a function or find the saddle points. We're going to calculate, we're going to find critical points and then test by looking at capital D equal to fxx times fyy minus fxy squared. Yeah, grab this example here. So let's look at one example quickly, because I do want to say one other thing. So let's say we have the function f of x, y equal to, I don't love that one. Sure, let's do this one. X times 6 minus 8x minus 6y. Seems kind of funky. I would probably multiply it out if it was given to me this way. I would probably write it as 6x minus 8x squared minus 6xy. So let's find our partial derivatives. Fx is going to be 6 minus 16x minus 6y. Gross. So that's equal to 0. Hopefully Fy is a little bit nicer. It is. Fy is 0 minus 0 minus 6x. Usually, you want to look at the equation that looks like it's easier to deal with. Clearly, that's the second one here. The second equation gives us what? X equal to 0. Is that a critical point on its own? No, it's not. You have to have a pair. So we go and we substitute this back in to the other equation, and then we get 6 minus 6y equal to 0, which means y has to be 1. So our only critical point here is the point 0, 1. And I think D is going to be relatively easy to calculate here. Let's see. Fxx is not exciting. It's negative 16. Fyy is also not. Oh, this is this is going to be interesting. Yeah. Okay. Now, so Fxx is negative 16. Fyy is 0. Minus Fxy is negative 6 squared. So our D is ending up equaling negative 36, which means we have a max, a mid, or a saddle. Saddle. When D is less than 0, we have a saddle. I'm going to say this now because it's going to be true later on, even though it's going to be a different context. When this D thing is the determinant of a matrix, of a 2x2 matrix. And I'm gonna say now, and I'll say it later. When the determinant is negative, when D is negative, that always means you have a saddle. So later on, when we're talking about spirals and nodes and saddles, and you find the determinant of your 2x2 matrix is negative, that's going to mean you're gonna have a saddle. It's a slightly different context, but it's a lot of the same meaning, which is kind of cool. So that example was not as exciting as I thought it was going to be. Oh well. Yes. So I'll remind you. So this is negative 16 is my fxx. So I just took the derivative of fx with respect to x again, and the 0 is fyy. Well, fy is negative 6x, so the derivative of that with respect to y is going to be 0 because there aren't any y's to give us anything here. Which is why I was worried, because if fxx, if one of them is 0, that whole part's 0, and so then if your other part is not is also 0, then you have problems. In fact, I will point out that this function, which is also not very exciting, x to the 4th plus y to the 4th, has one critical point. It's where you probably think it would be. Fx is 4x cubed. Fy is 4y cubed. You set those both equal to 0, and you only get the one critical point, x equals 0 and y equals 0. However, when you calculate D is 12x squared fxx times fyy, which is 12y squared, minus fxy, which is 0 squared. And when you plug in 0, 0, what do you get? You get 0 times 0 minus 0, which is 0. And we never talked about what happens when D equals 0. We talked about if it's negative, you have a saddle. If it's positive, you either have a max or a min, depending on the concavity. And when D is 0, that means the test is inconclusive. We don't know based on that value of D whether or not we have a maximum or a minimum or a saddle point locally. But if we look at the function f of x equal to x to the fourth plus y to the fourth, if you plug in any point other than x is 0 and y is 0, right? Again, if you plug in 0, 0, what do you get? 0. If you plug in any other point, is the function value going to be positive or negative? Always positive, meaning that a z value of 0 is the lowest possible value, and everything near it will be higher up. So we can see by inspection that this point has to be a local minimum because it has to be lower than all the points around it. So even though this test is inconclusive, we can see that 0, 0 is a local minimum. It's also an absolute minimum, but we're talking about local. Okay, I fear I haven't left myself enough time to really get to the meat of the next part, but that's okay. We can still look at one example. Sure. Oh yeah, we'll do that one. Yeah, we'll have to talk more about this next time. Well, let's say we want to find, we did this one. So now we want to talk about finding the absolute maxima and minima of a function. And yeah, we'll make it easy, since we only have so much time. Of f of x y equal to 5x squared plus 5y squared on a closed interval. I think your teacher likes to use in the notation omega. On the set omega, wow, I cannot do omega. That's terrible. Woo! Omega, which is equal to the set of all x and y, such that x is between -4 and 4, and so is y. You don't have to, but I like to draw the set. So here's my XY coordinate system. And like, here's y equal to 4, here's x equal to 4, here's y equal to -4, here's x equal to -4. And there's going to be so just like back in 17a, when you're trying to find absolute maxima or minima, you would find all the critical points, and then you would plug in all those critical points to the original function and also the end point into the original function to see which of them gave you the biggest value, and which of them gave you the smallest value. The same kind of idea is going to hold here, except that we have to test a lot more points. We have to test every corner point. We have to test any critical point. Let's see. So if I find my partials, fx is 10x, set that equal to 0, you get x equal to 0. Fy is 10y, set that equal to 0, you get y equal to 0. And then you also have to test any, so 0, 0, right? And then I wish I had these pictures with me because they're really, oh, actually, let me just, yeah. So you have to test any points along the walls. And here's what I mean by this. So let me just show you really quickly because it'll be faster than me drawing them. Sorry, 1 second. I promise we'll come back to this. Let me blow this up here. Grant, oh, come on. I told you guys I use Grant's website all the time. It's a great website. It's got lots of cool stuff. But one thing he has is some handouts. And the one handout I'm looking for here, yep, there we go, is the, yeah, cool, that one. So the idea here is that your surface might look something like this, where it's like peaked at the top, in the middle. And so your absolute maximum is in the middle of your domain, like right there at the origin in the one I just drew. But maybe the roof of your house doesn't look like that. Maybe the roof of your house looks like that, slanted upwards, so that the maximum is up in that corner over there. And the minimum is down in that corner over there. So you have to test the corners as well. Or maybe the roof of your house looks like that, where the maximum is not on a corner or in the middle, but in the middle of one of the edges, or the walls, as I like to say. So you have to test any critical point you find in the middle of your domain, any corners, and you also have to find any potential maxes or mins on the walls. So how do you deal with the walls? Well, here's how I deal with the walls. This wall here is the line x equals 4. So I'm going to plug in 4 for x. So watch this for a second. I'm going to have f of 4 comma y, which is going to be 5 times 4 squared. So that's 80 plus 5y squared. And then I'm going to take the partial. I should say this is x equal to 4. I'm going to take the partial with respect to y and get 10y equal to 0 is still going to give me y equal to 0. So the point 4 comma 0, right? Because I set x equal to 4 and I got y equal to 0. I also have a critical point there. In a similar way, this also would have been true if x was -4, right? It wouldn't have mattered if x is +4 or -4. I still would have gotten the same values here. So this is also a potential maximum there. And then my other walls are y equal to 4 or y equal to -4. And since they do give me the same kind of outcome, I'm just going to plug this in. So I plug in y equal to plus or minus 4. My function of x comma plus or minus 4 for y is going to be 5x squared plus 5 times positive or -4 squared. But that's going to be 16 times 5, which is 80. So that's 5x squared plus 80. And then my partial derivative here is going to be 10x, setting that equal to 0, because that's how we find the critical points. I'm still going to get x equal to 0. So since y was equal to plus or minus 4 and x is equal to 0, I get that point there at 0, 4, and that point there at 0, -4. So you often get every corner a point on each wall and at least 1 point in the middle. You don't always get all that, but sometimes you get more than that. And then after you find all those points, all those potential places where you have an absolute max and absolute minimum, then you have to plug them all into the original function. So if I plug in 0, 0, I'm going to get 0. If I plug in, I'm gonna cut my work a little bit short here, because I know that if I plug in +4 or -4, you still get the same result. If I plug in a plus or minus 4 for x and a 0 for y, I'm going to get 5 times 16, which is 80, plus 0, which is 80. If I plug in a 0 for x and a plus or minus 4 for y, I also get 80. But at the corners, if I plug in positive or -4 for x or positive or -4 for y, I get 80 plus 80, which is 160. So this function actually has 4 absolute maxima. They're occurring at each of these 4 corners. Let me show you why. I think you all want to see this picture. I know you're welcome to go if you need to go. If you give me just a sec, I think I can show you a picture that's worth your time. Let's go to Desmos real quick. Now, how am I going to do that? Yeah, okay, sure. So not Desmos, Desmos 3D. Don't you read my mind? Come on. How do I, okay, where's my graphing stuff? Sorry, I'm hiding it from myself. Okay, so I don't want to go, I'm not going to go quite that big just because it's really big. So let's just make it z equal to x squared plus y squared. And then plus y squared, James. And then if we look here, so it looks like that. And then if I look at some boundaries like x equal to 4, and we'll extend it that way. Oh, come on. I'll make things smaller. Sure. And then x equal to -2. So we're just making it a little bit smaller. Yes, I want to extend all of them. Y equal to 2. Sure. Y equal to -2. And then, so there's like our little square that we're living in. And you can see here, if you zoom out just a little bit, that, so look, like on the corners there, right there, right there, right there, right there, that's where the graph in that box is the highest. And then, right, oh, if I can make things translucent here, maybe it's a, sorry, I know I'm like, and then kind of in the middle, right? Oh yeah, oh, there it is there. Look at that. You can kind of see the in the middle red surface. It's the highest at the corners and then dips down, dips down, dips down, and then dips way down in the middle. So you've just got this part of the paraboloid and it happens to have the highest values at the corners, the lowest value in the middle. That's the idea of what we're doing. We're taking this red surface, but we're cutting it off into just this square piece and then seeing where the surface is the highest, where it's the lowest. That's the whole idea of finding absolute maxima and absolute minima on a closed domain. Okay, we'll talk more about that on Wednesday.